Okay, so the topic we want to start off with today is mixing solutions. I want to start out talking about solution concentration. Concentration of a solution is given by a percent. What does that percent mean? Well, a solution has two parts. A solution has a solute and a solvent. Now, the solvent is not what we typically think of as a solvent. It's not corrosive or doesn't, whatever. A solvent is just usually a liquid, but not necessarily, that other substances dissolve into. So if we're going to use salt water, the salt is the solute. Typically, the solute is the active ingredient. If we're talking about medications, it would be the medication itself. For you guys who are looking at a coolant, mixing it would be your lubricant and coolant additive that goes into it. Water is the solvent here. That is what the other substance is dissolved into. The solvent is basically a carrier. The scientific term is a vehicle. It's what carries that active ingredient where it needs to go. Now, water itself is a decent coolant. Why wouldn't you just use water? Not a lot of lubrication, but it would serve the purpose. But yes, the additives you put in it do aid in lubrication. What's the biggest reason why you don't use pure water? Metal machines, metal parts. Start splashing a lot of water on it, something's going to rust. So the additives you put into your coolant, one is slightly for lubricant, that is true. But the main thing is anti-corrosion, so that it doesn't, especially on any sort of equipment where there's moving parts, where any surface that gets worn or rubbed, corrosion would accelerate on those surfaces. Anything that gets hot. It's weird if you take a piece of metal and you heat it up. Interesting experiment if you've got free time, which I know we all have all sorts of free time, right? Take two pieces of mild steel so that it'll rust. Don't use stainless, obviously, because that won't rust. But set them side by side or hang them out in the weather, and just one of them go out there every day with a torch and heat it up until it starts to glow, and just walk away. And after a few days, that one that's been heated regularly will be rusted all to heck, and the other one will just be starting to rust. That heat cycle causes corrosion a lot faster. So the amount of the solvent, that's solute. Right, solute is the amount of solute in a solution. Tumbling already this morning. The amount of solute equals the concentration times the total amount. Now, there are a couple of different ways to measure this. There's actually three. One is volume by volume. So it's the volume of the solute or the active ingredient in the total volume of solution. The other is weight in weight, sometimes referred to as mass in mass if you're doing metric units, because metric system, we tend to measure mass instead of weight, where it's the weight of the solute and the total weight of the solution. The other one doesn't get used in machining. It's more of a medical application, and that is weight in volume, where it's the weight of the medication in the total volume of the solution. So we're going to do both volume in volume and weight in weight, which means whatever units we use for measuring the solute, going to be the same units as we use for measuring the total. That's very important because if they're not the same units, it's really difficult to define that concentration as a percent. Concentration is simply the decimal form of a percent. So it's a percent written as a rate. So if we have 400 milliliters, 16% solution. The amount of solute, or that active ingredient we have, 0.16 for 16% times 400 milliliters. Amount of solute per milliliters. We want to mix solutions. We mix solutions on something called conservation. Conservation is not like what we think of conservation as using as little as possible of something or maintaining something. What conservation are things that do not change, stay constant. When we're mixing solutions, there are two things that are conserved. One, total volume or weight. I have a certain amount of one solution and a certain amount of another solution. If I mix them together, I can just add those amounts. Second is the amount solute. First solution has 20 milliliters of solute. The second solution has 30 milliliters of solute. If I mix them together, the final solution has 50 milliliters. That active ingredient. Now, when I say that the volume or weight of the total solution is conserved, that does mean of the total solution. We do have to be a little bit careful of that. Like if we have if we're mixing the solution, like if we have, let's say we have 11 pints water, and to that we're going to add 2 pints of salt. We end up with 13 pints. No, we don't. Because what happens is those particles of water, even though we don't think of it as having gaps between the particles, water does. What makes a liquid is the fact that the particles are free to slide past each other. But it does not mean that there's no gaps in between them. There are. When we add the salt into that water, some of those salt particles hide in those gaps between the water. So if I have 11 pints of water and I add 2 pints of salt, it might go up to 11 and a half pints of salt water. There's a certain amount of salt. when you put the salt in there, when it fits in that gap, it might push the water particles a little bit further apart, but not much. So there's a certain amount of salt that you can add into water and not increase the volume hardly at all. So when I say volume is conserved, that's not what I'm talking about. But if I have one solution that's, let's say it's a 12% salt water solution. And let's say I have 4 pints of that. And I add that to 6 pints of 15% salt water solution. When I combine those, I will get 10 pints. Percentage will be a little different. And we'll actually look at how you find that percent in a minute. But if I add 4 pints of solution to 6 pints of solution, as long as they're close to the same, they do add up. The total volume does add up. The weight will always add up no matter what. Even if the volume doesn't fully expand, the amount of the weight does go together. Let's look at this example right here. Let's say we combine 4 pints, 12% solution, 6 pints, a 15% solution. What is our concentration of our resulting solution? Now first, I want to look at this problem and just analyze it a little bit. Which solution has a larger volume here? So which percent would we expect the final result to be closer to? Yeah, because there's more of it. In chemistry, there's something called the Lever law, where the more volume there is of one solution, the closer the final solution has to be to that concentration. We're not going to get into that. We're just going to do it the algebraic way here. So again, 2 things have to be conserved. One is total volume. I'm going to have my 12%, 8%, finding those to get who knows what percent. But my total volume, there's 4 pints of the 12%, 6 pints of the 15%. How many pints of our final amount should there be? Pints. Add up. Now the amount of solute also. It's the amount of solute that gives us the equation that we can solve here. We have the concentration times the volume, remember, gives us the amount of solute. So in the 12% solution, the concentration is 0.12 times the amount of solute, which is 4 pints. 0.12 times 4. 15% solution, the concentration is 0.15 times the amount of that solution, which is 6 pints. 0.15 times 6. That has to add up to give us whatever's over here. So it's going to be, I'm going to use X as my concentration times 10 pints. So this is the equation now that I can solve. 0.12 times 4, or 8. 0.15 times 6 is 0.9. X times 10 is 10x. I can add my 0.48 and my 0.9, 1.38. 10x. 0.138 x. 0.138, remember, is 13.8%. So now we need to make sure that we remember what x represents, and we need to make sure we've answered the question. X was the concentration of that final solution. That's the 13.8%. And we were asked what that concentration was going to be when we mixed it together. And it does make sense. 13.8 is slightly closer to 15 than it is to 12. Now, typically, we don't just want to combine two random solutions to see what we get, right? That's not how it works. We have a specific concentration that we want. Let's say we're going to ask how much 17% solution should be mixed with. You guys use milliliters in the shop, or do you guys use fluid ounces, or what do you guys use for you? You don't know? Whatever you feel like. What are the basins or the reservoirs in the machines measured? Do you have any sort of scale on them? Up till it runs over a little bit, then clean up the mess and get the over.
Yep, that's 7%.
So, how much 17% solution should be mixed with 120 milliliters? We'll use milliliters because they're easier to work with. Of 25% solution. Create 23. So our 23% is closer to 25%. Right? This is our desired result, the 23%. But whichever one of the ingredients, for lack of a better term, that we're going to mix, whichever one is the closer percent is the one that we're going to have more of. So if we have 120 milliliters of the 25%, we're going to have less than that of the 17%. 25% is closer to the resulting 23 than the 17. So we're going to mix 17%, 25%, in the hopes of creating 23%. That was the tricky part, total volume. The only amount we're given in this problem is 120 milliliters. That's the amount of the 25%. If I let X represent the amount of the 17%, because we're asked how much of the 17% solution. The amount of the 23%, remember, total volume is conserved. Those two numbers add together. This will be X plus 120. Then the amount of solute, remember, for each piece, concentration times the total volume or total weight. So the 17% is 0.17 times the amount is X. %, it's 0.25. Times the amount is 120. Notice I drop the units when I get into the equation, so we don't have to work with it. And for the 23% result that we're hoping for, it's 0.23 times that amount has to be X plus 120. Now we solve this equation. So the 0.7x or 0.17x, there's nothing to do there. 0.25 times 120 is just 30. 0.23 times x is 0.23x. 0.23 times 120, 27.6. What would we do next to solve this equation? The x to one side, good. Smaller one is the 0.17, so I'm going to subtract 0.17x, both sides. So I now have that 30 equals 0.06x. And of course the plus 27.6 is next step. Right, 27.6, good. It's 2.4 equals 0.06x. Then?
Item.
Now, we need to make sure we know what x represents. X was the amount of the 17% solution. So if x is 40, the units has to be milliliters because that's what the other amounts are measured in. Then is that what we were asked? Yes. We're asked how much of that 17% solution? Oh, 40 milliliters. Not so bad, right? Well, typically, we're not mixing two solutions. We're mixing one solution with a pure amount. We might ask how much water should be mixed with 140 milliliters of 18% solution to dilute it 12%. What we are mixing here, we are mixing water, otherwise known as 0% solution, with an 18% solution in an attempt to create a 12% solution. So our total volume, X is the amount of water. 240 milliliters is what we were given for the amount of the 18% solution. So the amount of that resulting 12% solution is X plus 240. So the amount of solute for water at 0 is the concentration times 18%, the concentration is 0.18, times 240 is the amount, equals 12% is 0.12 times an amount of X plus 2. As we go to simplify this, 0 times X, of course, is just 0. 0.18 times 240 is 0.2. 0.12 times X is 0.12X. And 0.12 times 240 is 28.8. And now we just solve the equation. 28.8, 4.4, 0.12x, is that correct? I think so. And we divide by 2. $36.66666. Not so bad. Of course, we do double check that 36.67 milliliters is the amount of the I made a bad mistake. 43 minus 28 is not 4, it's 14. I do 14 divided by 0.12, it'll be 20. That sounds more reasonable. After 31 weeks, you guys learn to just accept whatever I say. Understandable. At this point, the end of the tunnel is near. You're not looking at the writing on the walls anymore, right? So let's say we have a 12-quart basin, a reservoir. 12-quart reservoir tests at 35%. How much should be removed and replaced with pure, I should have said this is a coolant reservoir for a car, with pure antifreeze. To create 50%. So what we have here is we have 35% in the reservoir. We're going to add to that pure antifreeze, which is what percent? And we want to get to a 50% solution. here's the tricky part on this one. Total volume. When we are done, we're going to have a full reservoir. We can't have more than that. The reservoir is 12 quarts. When we're done, we're going to have 12 quarts of 50%. To accomplish that, we are going to remove a certain amount of the 35%. That's what we want to know, is how much we're going to remove. The amount of the 35% that is removed is X. I put the X in the wrong place, so that X is not described as 35%. That counts. We're going to replace that amount with pure antifreeze. So X is the amount that is removed, but then replaced with pure antifreeze. The amount of 35% that remains is the full 12 quarts minus however much we remove, 12 minus X. Now that's a little bit of a confusing setup. There's any questions on that? So then the amount of solute antifreeze (35% is 0.35 times 12 minus X. 100% is 1 times the amount of X. Equals 50% is 0.5 times that 12 quarts. So I'm going to do the 0.35 times 12, which I believe is 4.2. 0.35 times negative X is a negative 0.35X. We'll have plus the 1X, or just X if we wanted to. Now there's more I can combine on this left side, so I'm going to keep combining there. 4.2 isn't going to change, but a negative 0.35X and a positive 1X, a positive 0.65X. On the right side, 0.5 times 12 is just 6. Now we can solve the equation. Subtract 4.2. 0.65X equals 1.8. And we will divide by the 0.65. .77 quarts. We go back and check what does X represent. Well, that was the amount that we were going to remove and replace with pure antifreeze. So we would remove 2.77 quarts and replace it with pure antifreeze. So this would be in your coolant reservoirs. If you needed to change the concentration of the coolant, this would be what you would remove part of it and replace it with pure water, or remove part of it and replace it with pure coolant. Or if there was room in the reservoir, you would just add either pure water or pure coolant. What do you think? Good stuff? There's a worksheet posted in Blackboard. Unfortunately, I don't have it printed off. But you will notice at the end of the worksheet, it's a 3-page worksheet. There are 4 pages there. The 4th page gives you all the solutions, so that you can check your own answers and see how you're doing. Tomorrow in class, we will do a small worksheet together. I'll count that as the quiz. Those of you that didn't notice, by the way, on the test on Thursday, I did every one of those questions, except I changed one number and one question on Wednesday. Make sure you catch that if you're still working on the test. Okay, we'll cut off the recording there.